Okay. Consider a tumbler full of water. Assume this is filled with water. Now tell me, is water a rigid body?
No, sir.
Definitely not. A glass of water is not a rigid body. The particles of water move in different ways. Okay, and water can easily be deformed. Fine. But suppose the glass is full and you have to take it from one place to another without spilling water. Okay, let's say you have to take it from this position to some new position. I'll show you the new position also. Let's say it has to be shifted from one place to another. Maybe like this. Okay. Uh, you all imagine carrying this glass of water from A to B. How will you move it? I mean, definitely there will be displacement. Will there be rotation of the glass?
No, sir.
It's a full glass and you want to shift it from position A to position B without spilling water. So can you rotate the glass? You cannot. Fine. So keeping the orientation as it is, you will have to slowly take it to position B. Fine. This is what we mean by translation. Okay. Let's mark some points on this system. Let's call this as 1 point. This as another one. You can take a third one somewhere here. Okay. Suppose the orange point, as the tumbler is taken from position A to B, suppose the orange one went along this path. Okay. Aishwarya, tell me, how would the green dot have moved? Let's say we marked 3 dots on that tumbler. How would the green dot have moved?
So the same way A dot moved.
Okay. So the shape of the path will be the same. Where it started from and where it ends is different, but the shape of the path it takes is the same. The path, you can say the paths are parallel. Okay, I'll just copy paste it, change color. Because we are not rotating the tumbler. Without rotation, if you have to take it from this position to this position, you will have to take it this way. I mean, the particles will have to move along paths like this. The green dot reaches here. And similarly, the purple one also. Okay, are you all able to visualize this, how it is being moved from one place to another? Rishi, is this clear?
Yes, sir.
Okay. So these are the paths traced by these objects, by these particles, and they are parallel paths as you can see. Okay. At any particular instant, let's suppose this point. At this position, the orange dot would have been moving in this direction. Velocity of a particle is always tangential to the path that it follows. At that instant, the velocity of the orange dot is in this direction. Let's call this particle's mass as m1 and its velocity here as v1. Okay. The green dot, let's call it m2. When the orange dot is here, the green dot would have been here and it would have been moving with some velocity in this direction. Let's call it v2. And the purple dot would have been somewhere here. It would have been moving with a velocity like this, v3. Can any of you tell me a relation between v1, v2 and v3? Do you think they should be same or they can be different? Rotation is not allowed. So should the velocities be same or can they still be different?
Sir, they can be different.
How? Tell me, Rishi, you tell me, which of these can be greater than than which other? You said they can be different. Okay, listen. Actually, we have to go back to the discussion on rigid bodies. Yeah, this one. In a rigid body, the distance between two particles is not allowed to change. For that to be constant, for that distance to be constant, their velocity components parallel to the line connecting them must be equal. VA parallel should be equal to VB parallel. Perpendicular to the line joining them, they can have any amount of velocities. But what will those perpendicular velocities do? Those perpendicular velocities will make that line connecting them rotate. Okay. If B has a velocity perpendicular to the line connecting A and B, then B rotates around A. Similarly, if A has a velocity perpendicular to the line joining A and B, A will rotate around B, because we know in circular motion, okay, when an object moves along the circle, let's say there's one particle at the center, call it A, another particle on the boundary, call it B. Without the distance between them changing also, they can move. But if they have to move, their relative velocity has to be perpendicular to the line joining them. And if that relative velocity is there, perpendicular to the line joining them will rotate. Now, the situation that we are talking about is the motion of the tumbler. We want to shift it without spilling any water. So the rotation is not allowed. If rotation is not allowed, for any two particles, relative velocity perpendicular to the line joining them also should be 0. Along the line joining them, relative velocity should anyway be 0 because it's a rigid body. And because rotation is not allowed, there should not be relative velocity perpendicular to the line joining them also. So if you consider two particles x and y, okay, suppose x is traveling with some velocity like this. Let's call it Vx. You can imagine the line connecting x and y. Vx has a component parallel to this line. Vx parallel, I'll call it. Now y also could be moving, and y also must have the same velocity along this line. Vy parallel should be equal to Vx parallel. Why? Because if they are not equal, the distance between them will change, which is not allowed in a rigid body. Next, x could be having a velocity perpendicular to the line joining them also, Vx perpendicular. Now, due to that component, x tends to rotate around y. But if rotation is not allowed, or if rotation is not happening, then you can tell for sure that y also must have had equal amount of velocity in that direction, such that their relative velocity in that direction is 0. Actual velocities are equal, means relative velocity is 0. Fine. So relative velocity along the line joining them should be 0, means these two must be equal. This is from the condition of rigid body. Relative velocity perpendicular to the line joining them should be 0, means these two components should be equal. This is from the condition of no rotation. Now, if parallel components are equal and perpendicular components are also equal, it's like x components and y components are all equal, then the vectors themselves are equal. That means velocity of the first particle is equal to velocity of the second particle, is also equal to velocity of the third particle, equal to velocity of any particle of the system. Is this logic clear to all of you? Why their velocities must all be equal? Vanilla, did you understand?
Yes, sir.
Okay. So in a rigid body, for any two particles, the velocities along the line joining them must be equal, velocity components along the line joining them. And if no rotation is happening, the velocity components perpendicular to the line joining them also must be equal. Now, parallel components, perpendicular components are both equal, means the velocity is equal all as a whole. This is what we call translatory motion, pure translation. Okay, it's also called as pure translation. Means no rotation. So in pure translation, what happens? All the particles move in the same manner. The way they move can change from time to time. Okay, for example, initially, if you can observe in the diagram, initially they all started moving to the right side. Okay, they're all moving in the same manner to the right side. Afterwards, they are moving in some other direction. Okay. So time to time, how they are moving can change, but point to point, how they are moving should be the same. All points should have the same velocity at a given instant. Next instant, that velocity can change. It should change for all particles in the same manner. Okay, that is what is called as translatory motion or pure translation. So we can conclude that in pure translation, all particles must move in the same manner. That means velocity of the first particle must be equal to velocity of second particle must be equal to so on up to velocity of the nth particle. Now this velocity can change from one instant to the next instant, but the same change should happen for all the particles. That means their accelerations also must be equal. A1 should be equal to A2 should be equal to so on up to AN. All particles must have same velocities and same accelerations at all times. Okay, that kind of motion is what you call as translatory motion or pure translation. Now one of you tell me, if all particles have the same velocity, what will the velocity of center of mass be? Suppose all particles have a velocity of 20 I cap. All the n particles of the system have the same velocity 20 I cap. What will the velocity of the center of mass of such a system be?
20 I cap only, sir.
The same. Okay, you can answer that by using the formula for velocity of center of mass. Aishwarya, can you quickly tell me the formula for VCM?
So summation mi vi by total mass.
Correct. So it becomes m1 v1 plus m2 v2. I am representing all their velocities with v. Okay, the common velocity that they all have. So on up to mn vn divided by m1 plus m2 plus so on up to mn. Now in the numerator and denominator, m1 plus m2 so on up to mn is common. It will get cancelled. You will be left with v itself. What does this prove? This proves that if all particles have the same velocity, then center of mass also will have that velocity itself. Okay, same with acceleration. You can equate all their accelerations to a, and that will be equal to the acceleration of the center of mass. The common velocity they have is equal to the velocity of the center of mass. Okay, translation is an easy case actually, and till now, starting from kinematics, motion in straight line, motion in plane, loss of motion, work energy power, all chapters, the kind of motion we considered is translation only. We never took into consideration rotation of an object. If there's a block, the entire block moves in the same manner. If there's a car also, we assumed the entire car moves in the same manner. Okay, the entire mass of the car has the same velocity is what we used to assume. So till now we only consider translation. Okay. Now in translation, first, there are infinite particles in this system. Okay, but they all have the same velocity. They all have the same acceleration. So things kind of become easy in translation. Can one of you tell me how to express linear momentum of a system? What's the basic formula for linear momentum? Basic formula for
MV,
linear
sir.
MV. Okay. So we are now dealing with systems of particles. Okay, a system having infinite number of particles. So if you want the total linear momentum of the system, it will be m1 v1, that's the momentum of the first particle, plus m2 v2, that's momentum of second particle, so on, mn vn, that's the momentum of the nth particle. And this term appears in velocity of center of mass. We had discussed this before also. So this whole thing is the linear momentum of the system, which can be expressed as total mass of the system multiplied with the velocity of its center of mass. And that you can do in any kind of motion, not just translation. Therefore, momentum of a system can be written as total mass of the system multiplied with the velocity of its center of mass. Okay, this is true in general. We didn't use the fact that there is translation happening or anything. Okay, next. Kinetic energy. One of you tell me what is the basic formula for kinetic energy of a particle, single particle?
Half mv square.
Half mv square, correct. Now suppose there is a system of particles. Then you will have to take half m1 v1 square plus half m2 v2 square, so on up to half mn vn square. That is how you find out the kinetic energy of a system of particles. But suppose the system is undergoing translation. Okay, in pure translation, v1 v2 so on up to vn, they are all equal and they are all equal to velocity of center of mass, right? Therefore, kinetic energy in pure translation, T stands for translation, can be expressed as half m1 v square plus half m2 v square, so on half mn v square, where v is the common speed that they all have. And half and v square can be taken common. You will be left with m1 plus m2 so on up to mn, which is nothing but the total mass of the system. Therefore, kinetic energy in translation can directly be written as half into total mass of the system multiplied with velocity of center of mass squared, or I should say speed of center of mass squared. Basically, they all have the same speed. Okay, means the entire system's mass has the same speed. Therefore, you can use half mv square directly. And this is what we had been doing also in the chapter work energy power. Okay, so for a system undergoing translation, all the formulas that we derived or used till now, they are applicable. Now consider a different kind of motion. Pure rotation. What do we mean by pure rotation? Rotation around a fixed axis. Okay, like in the first lecture of this chapter, yeah, we had considered some rotating systems. You can take that giant wheel or you can take the fan also. Let us use the fan as an example. Now, suppose you are looking at the fan from below. Okay, this is a ceiling fan, obviously. You are looking at it from below. You can imagine a straight line, or that rod of the fan will be there, no? By which it is suspended. Okay, that rod is basically a straight line passing through the center of the fan. That rod is called the axis of rotation. Okay, like generally, what do we mean by axis of rotation? In a rotating system, no? If you trace the paths followed by all particles, they will be circles. Okay, all particles will move in circles. All those circles will have their centers lying on one line. That line is what you call as axis of rotation. Okay, just a moment, I'll show you an example. Like, yeah, you all must be knowing the Earth's rotation, right? Earth rotates about an imaginary line. That line becomes the axis of rotation of the Earth. Okay, in case of a ceiling fan, that suspension rod itself is the axis of rotation. So basically, if you trace the motion of this point on the Earth's surface, it follows a circular path like this. The center of the circle is here. Okay. Any other particle also, if you trace, follows a circular path like this. This is the center of the circular path of that particle. So like that for all particles. Okay, you can take a particle inside also, not an issue. Earth is a solid sphere. So this particle will follow a circular path somewhat like this, for which the center lies here. Okay. So the centers of the circular paths followed by all the objects lie on a straight line. That line is called the axis of rotation. Okay. And When do we call it as pure rotation? When the axis of rotation is fixed. Fixed means it must be stationary. So you all tell me, is the Earth's motion pure rotation? Is it rotating about a stationary axis in space? Is the Earth's motion pure rotation? Indirectly asking, is the axis of rotation of the Earth stationary? Pawan, what do you
Sir,
think?
no, sir.
Okay, Rishi will discuss. Pawan, what do you think?
Sir, yes.
How do you justify that? Why do you think the Earth's axis of rotation is not moving? Is Earth
Sir,
not
మొత్తం
moving?
అంటే
Huh.
ఎర్త్ మోతుంది కానీ సార్ దాన్ని సెంటర్ మనం ఒకటే తీసుకుంటాము
Center?
ఒకటే తీసుకుంటాం కదా సార్
See, center is one point only. I'm asking, is that point moving or not?
పాయింట్ మూవ్ అవుతుంది సార్
And also, we are not talking about the point now. We are talking about the axis of rotation. Earth ఒక axis చుట్టూ rotate అవుతుంది కదా, నార్త్ సౌత్ యాక్సిస్ చుట్టూ. ఆ ఇమాజినరీ లైన్ స్టేషనరీగా ఉంటుందా, అది కూడా కదులుతుందా?
కదులుతుంది సార్
దేని చుట్టూ?
యాక్సిస్ చుట్టూ
How can axis go around the axis? Pawan, imagine Earth moving in space. Okay, imagine yourself looking at the solar system from outside. Earth ఎట్లా move? How does the Earth move? Is it only spinning or is it spinning and also moving?
సార్ స్పిన్నింగ్ అండ్ మూవింగ్
Spinning and moving. It spins around its axis and that axis moves around the sun. Revolution కూడా జరుగుతుంది కదా. Okay, so Pawan, you tell me, is the Earth's motion pure rotation? అంటే axis of rotation stationary ఉందా?
నో సార్
The answer is obviously no. Okay, Earth does not execute pure rotation. It rotates around its own axis, but the axis keeps moving around the sun. Okay, that is called combined translation and rotation. Fine. Anyway, why I took the example is just to show you that there is something called axis of rotation. Fine. Use of you tell me, the motion of a ceiling fan as observed by someone in the room, is it pure rotation or not?
Yes, sir.
It is. Okay. Aishwarya, do you agree with this?
Yes, sir.
Okay. Ceiling fan, the moment you switch it on, the particles of the ceiling fan will start rotating, but that rod will stay there only. No, it won't move. Okay, it won't even oscillate. It's not an oscillating fan. Fine. So ceiling fan or the particles of a ceiling fan execute pure rotation. Okay. Now imagine that kind of a system. Imagine a system which undergoes pure rotation. Can any of you give me some more examples of pure rotation as observed by us in daily life? Only spinning should be there, but net movement should not be there.
Sir, the Ferris wheel.
Ferris wheel or giant wheel. Okay, good. Any other examples? Okay, fine. Find some examples later. It's not very difficult. Okay. Now see, let's consider some particles of this ceiling fan. Consider this yellow particle, sorry, orange particle. Let's say its mass is m1. Consider this yellow particle, assume its mass is m2. And then this blue one, assume its mass is m3. There are infinite number of particles here, okay? And all these are, what do we say, rotating around an axis, and axis passes through the center of the fan. Okay, we'll have to show it like this. This line passing through the center of the fan around which all these particles rotate is what you call as axis. I placed a cross there. Cross means there is a line perpendicular to your screen. Okay, or there's an axis perpendicular to your screen. That is what it means. Okay, fine. Now in pure rotation, all these particles will be executing circular motion around this axis. And as you can clearly observe, each particle can have a different radius in which it rotates. M1 rotates in a radius R1, M2 rotates around that axis in a radius R2, M3 rotates in its own radius R3. Okay, if you want, I can show you those circles also. The circle that M3 follows is this, roughly. The circle that M2 follows is somewhat like this. Okay, they all move along different circles. Of course, there could be some of them moving along the same circle also. Right. So, Vanilla, tell me, do you think all these particles will have the same speed?
No, sir.
Definitely not. Which particle out of these three? Okay, I'll write the order also here. The radius R1 is greatest, followed by R2, followed by R3. So M1 is farthest from the axis, followed by M2, followed by M3. So one of you tell me, or Vanilla, you only tell me, which of these particles do you think will be moving the fastest, and how do you justify that?
M1, sir.
M1 will be moving the fastest. Why do you say so?
Yes, the most in a given amount of time.
Correct. You use that word, given amount of time. See, this is a rigid body, no? By the time M1 completes one revolution, okay, M1 completes one circle, the other particles also would have completed the circle. Means they all rotate at the same rate of rotation. Rate of rotation is same means what? Angular velocities are same for all of them. Okay, that is from the condition of rigid body itself. This we had discussed before also. Angular velocity of the first particle should be equal to angular velocity of second particle, so on, should be equal to angular velocity of the nth particle. Okay, but when it comes to linear velocity or linear speed, in circular motion, we know linear speed and angular speed are related as V is equal to R omega. Therefore, V1 becomes R1 omega. Okay, let's call the common omega as omega itself, which is common to the entire system. So V1 becomes R1 omega, V2 becomes R2 omega, and so on. Vn becomes Rn omega. So the particles can have different speeds depending on the distance from the axis. Now out of these three particles that were given to you, R1 is the greatest distance. So if R1 is greatest, V1 will be the greatest. Okay, among those three particles. Okay, fine. Now for this kind of a system also, where different particles have different velocities, the total linear momentum of a system, of the system, is still M1 V1 vector product, sorry, vector sum, M2 V2 so on up to Mn Vn, which is still equal to total mass multiplied with the velocity of center of mass. This can always be used. Momentum of a system is the momentum of its center of mass. Remember it like that. Okay, irrespective of the kind of motion that the system executes. Let it be. Can one of you tell me, for an actual ceiling fan, what is the net momentum? Or where do you think its center of mass lies? Where does the center of mass of an actual ceiling fan lie?
Sir, it's center.
Center or maybe on its axis. Okay, usually most likely it is at the center of the fan itself. Now you all imagine the fan rotating. Okay, let's say it is switched on. Irrespective of what speed it is rotating, it is rotating. Does the center move?
No, sir.
No. Therefore, what is the velocity of center of mass of the rotating ceiling fan?
0, sir.
0. And if center of mass velocity is 0, what is the total linear momentum of the rotating ceiling fan? It will be 0
0, sir.
itself. It will be 0 itself. Okay. I'm not saying for every rotating system momentum is 0, but for ceiling fan it is definitely 0 because there is symmetry in that case. Center of mass lies on the axis of rotation. Okay, therefore its linear momentum is 0. Okay, let me give you one problem based on this. So now you understand that irrespective of the type of motion of the system, its total linear momentum is always total mass multiplied with the velocity of center of mass. Okay. Let's say there is a rod like this. Okay. Assume it is pivoted, okay, at an axis somewhere here or about a point somewhere here. What does that mean? That means the rod is free to rotate around this axis, but that axis should not move. So it's kind of like this. Okay, for example, this pen, suppose I clamp it here. Okay, now I'm restricting it to rotate like this. This point of the pen remains stationary, the other points move. Okay, you can assume this red line that you see, red band that you see as its center of mass. So it's not hinged at the center of mass, it is hinged somewhere else, or it is pivoted somewhere else. So it rotates like this. Center of mass is also moving, as you can visualize. So this line, this imaginary vertical line through this point becomes the axis of rotation for this rod. Okay, the rod is spinning around that axis. So you have to imagine a straight line like this, y-axis. The rod is rotating around that y-axis. Okay, but the hinge point is here, it's not at the center. Okay, so imagine a rod like that. So where exactly is it? Let's say the total length of the rod is L. Little bit of calculation you'll have to, small minor calculation only. Let's say total length is L. And the rod is spinning with an angular velocity omega. And where is it pivoted? It is pivoted at a distance of L by 3 from one end. One of you tell me, where is the center of mass of a uniform rod?
L by 2.
L by 2. So this pivot is not at the center, not exactly at the center. So at some instant later, the rod will be in this orientation. Okay, some more time later, the rod will be oriented like this and so on. That is how it is rotating. Calculate the linear momentum of this rod, total linear momentum. Think carefully and solve. Okay, that's a good thing to ask. Assume the mass is m. Mass has to be given. Total mass, take it as m. Okay, I got one answer as m L omega by 6. We'll see. Pawan, how are you trying to solve this?
Try good, sir.
Okay, fine. Yusuf, how are you trying to solve? Rishi?
Sir,
Okay,
I'm
fine.
not sure.
Fine. Rishi, you tell me, what kind of motion is this rod executing? Translation or rotation?
Rotation, sir.
Rotation. Okay. And irrespective of whether it is translation or rotation, how do you or how can you always express the total momentum of a system? What is the general formula for total linear momentum of a system? It is total mass of the system multiplied with the velocity of its center of mass. Okay, system consists infinite number of particles. Each particle could have its own momentum also. Okay, each particle could be moving with a different velocity, but the total momentum of a system can always be expressed as total mass into velocity of center of mass. So all you need to find out in this case is the velocity of its center of mass. Okay, Aishwarya, where is the center of mass of the rod?
L by 2, sir.
L by 2. And where is it pivoted? It is pivoted at a distance L by 3 from one end of the rod. Okay, so this is the pivot. Fine. So every particle of the rod will be moving in a circle around this pivot. Okay, around this axis actually. You have to imagine a line perpendicular to your screen passing through that pivot point. That becomes the axis of rotation. Now let me mark the center of mass of this rod. Center of mass will be at L by 2, that is the midpoint of the rod. The green dot, which is the center of mass, will be rotating along a circle like this. Okay, we need to derive an expression for velocity of this green dot. That is the velocity of center of mass. Okay, Aishwarya, tell me, in circular motion, how do we express velocity in terms of omega or speed in terms of omega?
Sir, R omega.
V is equal to R omega, correct. Where R is the radius in which that particle is moving. So this distance is what we need to find out now. Once you know that, you can write VCM is equal to R omega. Okay. The total distance from one end to the center is L by 2. This complete distance is L by 2. From that you remove L by 3. What remains is R. So R is equal to L by 2 minus L by 3, which is L by 6. That's all. R is equal to L by 6. Therefore, the total momentum of the system becomes M L by 6 into omega, or M omega L divided by 6. Is this clear to all of you? Rishi, did you understand?
Yes, sir.
Pawan, got it? Yusuf?
Yes, sir.
Yes, sir.
Okay. So you should look for how the center of mass is moving. Then you can tell the total linear momentum of the system. In this case, the rod was not hinged or pivoted at the center. It was pivoted at some other point. So the center also will be rotating now. Center of mass will be rotating. Let it rotate. It moves in a circle. So using the formula in circular motion, V is equal to R omega, we got its velocity. And with that velocity, we are expressing the total momentum of this system. Okay. Fine. So whether it's translation, rotation, or any kind of motion, momentum of a system is always mass multiplied with velocity of center of mass. Okay. Next is kinetic energy. Okay, listen, this is where we start deriving another quantity. Now this is a rotating system of particles, right? Kinetic energy of a single particle is half mv square. Now this object has infinite number of particles, and since it is rotating, different particles will have different velocities. Therefore, kinetic energy has to be calculated like this: half m1 v1 square plus half m2 v2 square. That's the kinetic energy of the second particle, and so on. Kinetic energy of the nth particle. Is there anything we can take common in this equation? Nothing. We can't take m common. We don't know if all the particles have the same mass or not. And definitely we cannot take the speeds common, because Each particle will be having its own, could be having its own speed. V1 is equal to R1 omega, V2 is R2 omega. So only half is, like you can take the term half common if you want, nothing else can be taken common. Does that mean to express kinetic energy of a system of particles, we have to add infinite terms? That is impractical. But we need a way to express the kinetic energy, because otherwise how will we find out energies of rotating systems? Okay. So what we do is we try to express this in some common terms. Tell me, one of you tell me, for a rigid body which is rotating, what is common for all the particles? Which physical quantity is common to all the particles? It's written on the screen.
Omega.
Omega, angular velocity, is common for all the particles. So we will express these in terms of omega. And the only thing we can do is write V1 as R1 omega and square it. V2 as R2 omega and square it. So on. Vn as Rn omega and square it. One of you quickly tell me, what are R1, R2 and so on? What are they?
Distance between the particle and axis of rotation.
Good, good. R1 is the distance of M1 from axis of rotation. R2 is the distance of M2 from the axis of rotation and so on. Okay. Now in all these terms, omega square is common and half is also common. Therefore, kinetic energy of rotation or of a rotating system can be expressed as half. Omega square is common in all of them. What are you left with? M1 R1 square plus M2 R2 square, so on, Mn Rn square. This term in a simplified manner can be expressed like this. It's the summation of Mi Ri square, where I varies from 1 to n. And this summation, sigma Mi Ri square, is what we call as moment of inertia of a system. Very, very important quantity, moment of inertia. Okay, we'll be using this in other chapters as well. Anywhere where a particle undergoes rotation, you can talk in terms of moment of inertia. So if that entire bracket is represented by the symbol capital I, you can therefore write kinetic energy in rotation as half I omega square, where I is the summation of Mi Ri square. And this is what we are going to work on over the next few classes. How to find out this quantity for a system. Because without that, you can't write the kinetic energy of that system. Then you can't find out anything about that system. In fact, not just kinetic energy, you'll be using this term I in other situations as well. Okay, you'll learn. In this chapter itself, you'll learn. But let's first understand the meaning of this quantity. Can any of you tell me what is inertia?
So the inability of the body to change its state of rest or motion.
Correct. You can say it's the tendency of an object to continue doing what it is doing. If it is at rest, it has a certain tendency to continue to be at rest unless disturbed. Okay. Or you can also say it is the resistance offered by an object to a change in its state of motion. So suppose something is at rest. Inertia is basically how difficult it is to move the object from the state of rest. Okay. Fine. So there is inertia of rest, there is inertia of motion. These two we had discussed earlier. Okay, one of you tell me, what is the measure of inertia of rest? Simple, simple visualization. Suppose there are two objects. Okay, you can take one as a small stone, the other one as a big rock. Let's say both of them are at rest. Which is easier to move? The stone is easier to move. Means it has less inertia. The rock is more difficult to move. Means it offers more resistance to change in state of rest. Stone offers less resistance. Means stone has less inertia. Rock has more inertia out of these two. What is the difference between the stone and the rock? Mass. Okay. So inertia of rest is given by mass of the system. Whichever object has less mass has less inertia of rest. Means if it is at rest, it is easy to make it move. Okay. Next, there's something called inertia of motion also. If an object is moving, it tends to continue in its state of motion unless disturbed by an external force. Now you consider two identical objects, identical in terms of mass. Okay. Let's say one is going with a small speed, some 2 meters per second. The other is going with a high speed, some 20 meters per second. Which is easier to stop? A or B?
A, sir.
A is easier to stop. Means changing the state of motion of A is easier than changing the state of motion of B. Now, what is the difference between A and B? You may say velocity. It's actually not velocity, it's momentum. Mass multiplied with velocity. Okay. So momentum is a measure of inertia of motion. Anything which has more momentum has greater tendency to continue in that state. Anything which has less momentum has lesser tendency to continue in that state. Okay, so momentum is a measure of inertia of motion, you can say. Linear momentum is what we are talking about. Okay. Now these two are for translation. If you want to give velocity to an object or change velocity of an object, these are the measures of inertia of rest and inertia of motion. Same thing can happen in rotation also. And in rotation, the inertia of rest is given by this quantity that we are now talking about, moment of inertia. So basically, moment of inertia is the tendency of a system to resist rotational motion. Okay, greater the moment of inertia, greater the inertia of rest in terms of rotational motion. Means more difficult it is to make the system rotate. Lesser the moment of inertia, easier it is to make the system rotate. Fine. So moment of inertia is nothing but rotational inertia of a system. And just like linear momentum, there's something called angular momentum. So for rotational motion, object will have a tendency to continue its rotational motion. No? If you want to change that rotational motion, the measure of rotational inertia in motion is given by angular momentum. You learn this quantity in this chapter itself. This is a very big chapter actually. In your entire syllabus, 2-year syllabus, system of particles and rotational motion is the biggest chapter. You'll come across many new quantities. You'll look at a whole different way of analyzing systems. Okay. So we'll go through this slowly only one by one. So for now, what we are going to focus on is moment of inertia. So what's the basic formula? I is equal to sigma mi ri square, where mi is mass of one of the particles of the system. Ri is distance of that particle from the axis of rotation. Fine. So derive the SI unit and dimensional formula of this quantity quickly. All of you type your answers in chat. What is the SI unit of moment of inertia and what is the dimensional formula of moment of inertia? Okay, see, sigma is summation. It is just addition of terms that won't disturb the dimensions. So basically moment of inertia is mass of the first particle square of the distance plus so on up to mass of the nth particle square of its distance from the axis. So all these terms are simply mr square terms. Whatever is the unit of the first term, same will be the unit of all other terms, and same will be the unit of moment of inertia also. Okay. Now mass multiplied with square of distance becomes kg into meter square. That's all. Therefore, SI unit is kg meter square. Dimensional formula for mass is m. Dimensional formula for length is L. It is getting squared. So the dimensional formula for moment of inertia is ml square. Okay. Now let's calculate moment of inertia of some systems. For today, we will only deal with systems which are collection of point masses. And I'll just give you an introduction of how to calculate moment of inertia for a continuous mass distribution also. Fine. Suppose there are 3 particles like this, and there is an imaginary axis somewhere here. Let's say their masses are given to you. Assume this is 2 kg. It is at a distance of, or okay, let's assume they're all along the x-axis. They're all lying on the x-axis. Fine. Let's say this one is at x is equal to -2. This is at x is equal to 2. And this is at x is equal to 5 meters. All these are in meters. And mass is 2 kg. Take this as 3 kg. And the last one, take it as 1 kg. Calculate total moment of inertia of this system. So it's a very simple addition. M1 R1 square plus M2 R2 square plus M3 R3 square. Do it, all of you. I want answers from everyone. You just have to take each mass and multiply it with the square of the distance from axis. Now I have to tell you which axis I want. Assume this is the axis. Okay, the y-axis. You have to find out moment of inertia about y-axis. Okay, with respect to y-axis is what I mean, but generally we call it about that axis. Okay, it's called like that. That means you have to take distances from that axis. I got one answer as 45 kg meter square. We'll see. Okay, Rishi, how are you trying to calculate this? Shouldn't take this long.
Sir, 6 into
Huh? Why are you combining all the mass? Pawan, how are you trying to calculate this?
Sir, 45.
Okay.
2
See,
into -2 whole square.
you should not take -2. It's the square of distance, no? So 2 square only you'll have to take. Anyway, okay. So it's a 3 particle system. Let's call the masses as M1, M2, and M3. And their corresponding distances from the given axis will be called R1, R2, and R3. You just have to apply the formula. I is equal to M1 R1 square plus M2 R2 square plus M3 R3 square. Yusuf, this is how you are supposed to do it. Okay. M1 R1 square, 2 kg into that distance R1 is 2 meters. Okay, it's the coordinate is -2, but the distance is 2, you square it. -2 squared or 2 squared is the same anyway. So 2 into 2 square, 8 plus M2 mass is 3 kg, distance is 2 meters. So 3 into 2 square, 3 into 4, 12 plus M3 mass is 1 kg, distance is 5 meters. So 1 into 5 square, 25. Totally 20 plus 25 becomes 45 kg meter square. That is its moment of inertia about the axis which you are asked. Okay, is this clear to all of you? Any doubts in this? Fine. Now for this same system, tell me how much is the moment of inertia about x-axis? I'll call it as Ix. Moment of inertia about x-axis, how much is that? Think carefully, type your answers in chat.